going to discuss about the title that I'm proposing about from a sparse data to reliable decision. From this title, I'd like to start to what material I'm covering in this webinar. I categorize them in two main parts as giving you a background on the site and data set that I like to work on applying the framework. And in part two, we'll delve into more detail about the framework. Then I'll summarize. Part one starts with the location. I'd like to give you some understanding and a background about the site that we are working on, stress data characterization. Here is Forsmark site in Sweden, eastern, close to the coastline and nearly above the city Stockholm, and is selected by SKB for deep geological repository for nuclear waste. And the first question as concerned with rock mechanics and rock engineering is, what is the stress state that we should select for our design and for that concerns the design process? Because in-situ stress in terms of rock characterization impact the overall stability and performance and safety of the such a critical infrastructure. When we start about doing site investigation for a deep geological repository, we start with doing some site investigation, like having boreholes, applying different method. And here I would like to talk about some borehole that you see a chronologically plot on right side that shows in y-axis the boreholes and timeline in right side. And what we mean by a stage is the campaigns that have been conducting in situ stress measurement by overcoring. And this means that data is accumulated over time and over 3 decades about this specific site. And as a result, if you see in lower panel, you will see that stress is more available and frequent at lower depth, like from 0 to 200. And we are discussing about 500 meters. And in full depth, we see that data is sparse. So as a result, we would like to get from more data for the benefit of sparse zone data, sparse data zones. There are some challenges with site characterization in terms of in-situ stress estimates, and because specifically here I would like to talk about Forsmark site and in-situ stress. We see variation and lots of different coefficient of variation, which it is inherently belong to data. And we can't change that, but we can understand and quantify them. So it is variability across range depth, and as a result, it will cause uncertainty in our estimates. And the challenge is we have different depth, different variation across depth. And here we would like to answer a core question that we arise from here. What do we move, how do we move from what data do we have to what precision do we need, and do we have enough the precision we need for the design and about the stress estimate as a design parameter. To get more familiar with overcoring stress data, because it's important we understand basically our overcoring, and it helps us to design our framework. We have 10 boreholes with a full depth about 500 meters, where it is expected that deep geological repository be located. And we overall have some overcoring, which it is during the quality check, we here selected and filtered 190 overcoring measurement. And to be more specific about the variation, here is a plot that shows you across depth and about the principal stress sigma 1, how varies across depth. If you look at the left side, that shows the depth from 0 to 500, and the increasing sigma 1 from left to right, we have different mean value for stress across depth. So it varies from 2 megapascal to at 500 meter about 60 over 60 megapascal. And another challenge is here. We have variation. It is not what we imply. It is exactly what the data directly tell us. What is the variation? Coefficient of variation is captured across depth. And is it right that we have a full pool to make an overall estimate of mean stress for a design? Of course, it doesn't make sense as an engineer who want to work on the design. So this concept help us to how to think about our problem, how to develop our framework. We develop a framework that is a combination of several tools that are building up using different algorithms, mainly by AI, Bayesian, and our understanding of the problem. And it is sequential. And here's the framework. It has different steps, and it starts with breaking the depth into using the transition zones into different zones that data are homogeneous. So we use some algorithmic AI pattern recognition, or could be kind of digital segmentation. And we do process the depth to break down into different zones. In a step 2, we are fitting some distribution. Traditionally, we enforce our model to have a normal distribution, which it is wrong, because for stress, which it is a critical parameter for our design, extreme value matters, which normal distribution rarely can capture that. So we make an automation of how the model select itself the distribution. Next step is our core contribution, because here is our hierarchical Bayesian pooling, which it takes some information from the data that we already have. Instead of drilling more, obtaining more data, to get more information for the zones that the data are sparse. And then by some predictive model evaluation kind of machine learning, we try to validate our model to answer some questions like how many measurements do we need for the precision and our credible interval target. So we start with step 1. We develop the model to segment the full depth profile. We use different segmentation algorithms like PELT, binary segmentation, bottom-up. Each of them have different application. The first one take the globally transition zones. Then we use binary segmentation, and the bottom-up is kind of clustering that takes the finer segments all together to capture the most homogeneous zones. And there are some rules. We apply the zones that overall have 30 percentages of agreement in all method that we are selecting. And we move these windows and screen depth with plus minus 30 meters, and the output will be the boundary location. And here are the depth profile. 500 meters, different depth zones. The first one is whatever that we obtain with the first simplest boundary detection. And when I say boundary, it's the transition zone for variation, not the geological or geomechanical domain because it needs its own validation. Here we talk about the data homogeneity. Second one works with a little bit more specific with binary segmentation, and it finds again agreement more accurate, and then with bottom up that they capture the agreement zones. And here are validated segment transition. The red line that you see across different depths, like 100, not 100, probably it could be 70 meter, and different zones that I'll introduce later, they are validated during a sensitivity analysis and bootstrap sampling. So here we agree that we have different zones with different specific uh, specification of data and frequencies. The next step is what distribution our data have. We are not enforcing our model to follow a normal distribution. We let itself decide what distribution it has, and we test it with some indices and metrics. The model says that the most dominant are Gumbel for mean and max tails and log normal. We have some also negative values, which they are valid, belonging to principal stress sigma 3. And we have some tails that it is the most important for a designer because it is what we use for an optimal design, for a safer design. We let the model decide which distribution is selected. And here is how we decide. We say that the lighter blocks which showing generally less than 4 and close to 0 best distribution for a specific zone. Like if you see the lower panel, it show S as segment 1, segment 2, segment 3, and also for 3 principal stresses. So here we let the model automatically decide which distribution is dominant. So we have to use mixture models. And then we can show how these distribution are here, which are employed from the AIC, which it is a way that we examine which model distribution is dominant. And it uses, in fact, the differences between the best fitted distribution and worst scenario and take the gap. The bigger gap, it means it's worse. And as a result, we take the lowest value of AIC as the best distribution model. So we take our distribution, and then we, as mentioned, we need to take this distribution, mixture distribution using AIC. I recommend you to use that because it automatically choose the distribution, which we later on use those distribution to build up our hierarchical Bayesian pooling, partial pooling. And then in the next step is the core of our framework. We employed different segments in full depth profile. Then we apply distribution, best distribution for our for pair segment, and the best for pair segment and each principal stresses, which they all go here to build up our best estimate of stress. And if you notice here, we have a stress estimate with full pooling. It means that we have a full pool overall mean stress and partial pooling. If we do partial pooling, we get a stress reduction, uncertainty reduction in stress estimate. And here this table shows that within segments 1, 2, 3, which we have higher amount of data is more frequent, we have less CI or credible interval reduction. However, for segment 4, 5, 6, which they are more in terms of data sparse, they get more and higher CI reduction and get reduced the uncertainty. To show you about the framework, overall, we design our population hyperprior in terms of what could be our mean and between zone variability based on the segments that we have on top. Then at level 2 of our hierarchical partial pooling framework, we build up the hyperprior for zone specific that it used the global mean from first level, and then we use those rules from the global mean from level 1 using a partial pooling factor to make estimates from our observations. So we make we do estimate each observation within these rules. I don't want to go through the detail, but this is what you need to make for based on your data and based on to do a partial pooling. So as we before mentioned, we have a full pooling. Full pooling means it's just conventional method. We take an overall mean for full depth, which is of course not the best option, and it's wrong. We do pooling based on partial pooling based on the segment. In this panel, if you notice, we have partial pooling in the right side from the main data without pooling and compare with the partial pooling. And if you notice, it shows that how our posterior mean with no pooling and with partial pooling, how the different are the credible interval, and it significantly reduces, as you see on the right side panel histograms. It shows that in segment 4, 5, and 6, the credible interval reduces, but when we do partial pooling, in fact, the partial pooling is the uncertainty that it shows in darker histogram in bar, and no pooling that has higher uncertainty with lighter color. It shows the no pooling. So here, during the partial pooling, we significantly reduce the uncertainty of our stress estimate, which it won't happen if we do an overall full pool in our conventional and traditional method. Building on the partial pooling, we can answer some questions like how much data is enough. So for that, we make some simulation, our target for uncertainty and precision. As a result, we break down our data in different population, like 20 percentages as the preliminary studies, then for 40 percentages, the more data comes, then 60 percentages and 80 percentages and full data. And our uncertainty target are as 10 megapascals to reduce to 3 megapascal when we consider more data available. And here it shows that with having with having the basic amount of data, like the about 20, as you see, the lower x-axis shows the number of measurements. It shows that within our estimates, so let's investigate how much data that estimates used, in fact, to reach that sort of target that we wanted. We would like for different stages, meaning different percentages of and availability of data. For stage 2, we have the target of 10, and here shows the target. So here we see initially less than the data that is, when the data is not a lot, we won't get that uncertainty and precision that we expecting. And here shows that what uncertainty targets are. So as the data are more available, starting from 0 to considering to reach to 80 data, the uncertainty target, we reach to uncertainty target that we have. So in other words, the precision that we would like, all are converging toward a specific precision. Most of them are below the target, meaning they have sufficient precision. And in right side, it also shows basically with the available data within the segment 1 to 3, about 300 meters, with already whatever that we have, we get that precision. However, for other zones, we need more data. That's why we need to do hierarchical pooling and get more information from the data that we already have. And finally, we want to do validation before we make a decision tree and decision rule for based on whatever that we learn. We would like to do a validation. So we take a stage 2, meaning the older campaign that we obtain some data from say 1980s to before 2000 in terms of the years chronologically. We take those data, build up the model, and based on the stage 2, we estimate the stress state for stage 3 before we observe stage 3. And then we compare our estimate with stage 3 to capture how much precise the model are. The first thing that we found is that stage 3 reproduces stage 2 predictions. And then another thing, we found that stage 3, after we use itself the stage 3, meaning the latest data plus the preliminary data that we obtained within stage 2 years ago, how data accumulation help to reduce uncertainty. So the more data, the more accurate the model are. If not, we do partial pooling. Another thing is that we found that if we do not partial pooling, we will miss some information that data have. For example, in one stage, in stage 2, in one borehole, we figure out that data is much lower than what it is in fact obtained in stage 3, and it is kind of a problem with probably operation, or from we obtain a data from a disturbed zone. So it means that we absolutely need partial pooling, because it helps us not only we get more information out of our data and help the sparse zone, and without even drilling more, spending more time. It also helps us to understand the problem that may be already in older data that they are available. All of these have been overall applied to make a complete partial pooling. So pooled here means a full pool, traditional way that we take an overall global mean for full depth, which it is showed on top in blue. Pool percentiles shows from 5 percentages, a wide range from 5 to 95 as the percentiles, from 5 megapascal to 45. We can't use this range. We can't use this mean value for a design, which it is the stress variation is different from the the shallower zone to the depth and full depth profile where DGR or Deep Geological Repository is located. As a result, and lower side, you see that where the circle is showing that how much the percentiles are different in the last part, in the last zone, the deepest part, with the overall blue pooled percentiles. So what will happen if we take those pool percentile in our design model for based on probability models? If we ignore those variation, uh, it is significantly different. We can't ignore that, and we should absolutely avoid taking global mean and pool percentiles. Uh, I don't go through the numbers in detail, that whatever that my analysis says. I'm mostly emphasizing how the framework works, how it shows that how we should think about our problem, our data, and the design requirement. Uh, Here is also another example that how in between the depth probably 220 to 370, the percentiles are different. The mean value 5 percentages and 95 percentile are different with whatever that blue line are introducing as the global mean. And finally, another example, as whatever that help us building up all whatever we have done so far using our framework, how we can use those as a decision making within our design. This figure on right side shows two red and green line. Red line is the precision, or say our target for a credible interval, while it shouldn't be more than that. It can be lower. Lower is better, but it shouldn't be more than that. Above red line, it means we need absolutely more data. Even modeling doesn't help. But here, using the framework, it shows we reach the target, we get more precision than we expected, which we can't get them using the conventional method. Instead, we can take with partial pooling. And overall, that's whatever it says. It says that you should do partial pooling, and at all stages and depth segments, you can reach the uh, precision that you need using the data that you already have without even adding more data. And this is the strategic decisions that you can extract from your framework after whatever you have done. This is what dynamic I'm currently updating this framework. This decision-making framework is automation of our work. It offers uh, how we ask. It's a sequential questions, and we ask if what kind of distribution our model has, and what kind of variation it has, how much data do we have, and per segment. And also we are adding which model works based on the multimodal if bimodal, or based on our coefficient of variation. And then it tells you that how you can keep moving during your site investigation and stress characterization. And here is the summary. This table shows left column what is site specific for me. Segment boundaries, the distribution that I've chosen. You're welcome to use further distributions for your extreme values. You can choose different, or you can estimate quantitatively the minimum sample size instead of deciding qualitatively or subjective decision making. And then you can make an automation. It is transferable to other application, not just for DGR, for other application, for infrastructure, for tunneling, or further problem, research problem, or industry problem that you may be working on. And overall, this is what I'd like to emphasize on overall framework. Do not pull heterogeneous data because it gives you a global mean, constant within depth, ignoring the variation that is it's tied to in-situ stress state, as you all know. And then use probabilistic model. Do not use only one distribution. Use mixture families. Use more innovative that be able to capture extreme values, because extreme values, it is what impact your design safety and overall stability. We need to appreciate hierarchical partial pooling, because we need to break down our model and be more precise at different stages of our projects. And that's how Bayesian active learning is. And we set an uncertainty, and we can ask how much data is enough and test if it is really enough, or we can offer that it is critical to obtain more data, or probably you don't need to because you already have the information in your database as is without doing anything further. And then you can gradually, by doing and updating your framework, strengthening your decision tree, and it is kind of automation, which it all have been so far left to the experts. So they have been doing manually so far. That's all here for today, and I appreciate Lena and ISRM and all audience. Thank you for listening to me. And here are some sponsors that I've been working so far, and we are still, this is part of our ongoing project, which we wish to update and work on further. Thank you, Lena.